Thank you. Good morning, all. So my talk is on using high throughput JPEG 2000 images as a default storage format for all clinical images, which include X-rays, ultrasounds, CT scans, and MRIs. So in clinical imaging, any image that we take is stored as a DICOM file, which is basically the image file that is combined with all the patient information and everything that is to do with the modality acquisition. What was the frequency of the CT? What was the intensity of the X-rays? All of these are bundled together as a single file. And the idea has always been that each of these images will be uncompressed because every little detail in a medical image is very important and could signify something. The idea has been uncompressed images for so long that TCIA, which is the Cancer Imaging Archive, currently has 30.9 million images, and all of them are uncompressed. And we've had lossless compression algorithms for a while now. JPEG LS, JPEG 2000, and currently HTJ2K, they've existed for a while. And for 30.9 million images, a compression algorithm can really bring down the size of these archives. So our tool is called DICOM HTJ2K, and it's pretty sequential, straightforward Node.js library. DCM.js and DCM.js imaging are third-party libraries that we use. Others are all in our repository. Chris Hafey, which is one of our co-authors, is the primary author of OpenJPEG.js. OpenJPEG is a C++ core that's also a third party, and we've built a wrapper around it because writing everything in Node.js makes it very easy for us to spawn off web browser enabled views at any point of time. But this flow is just for a single file. A single DICOM file will we start, we initialize the libraries, we read and note, do all the parsing, and we do our transcoding of the pixel data. But for a collection, which in broadly speaking, at least has 30,000 images, we cannot just keep doing one process in general. So we utilize hardware services at the UAMS high performance computer. And we have about 96 Xeon nodes, which work best for our purposes. We also have Xeon Phi nodes and a ton of GPUs. My work is only CPU oriented, but there has been another work using high throughput JPEG 2000 on a GPU. So I've currently chose something from Kaggle so that everybody can access on what it might look like for them. So if you go to this collection on Kaggle, which is the OSIC pulmonary fibrosis progression, this is a collection of CT images. Each of this image is about half a megabyte, and there are about 29,800 images there. And we bring them down by a whole size of 2.5. Now, imagine that you are a researcher that you host medical images. You have to report to the NIH. You hope someday people will download your data. And bringing it down by a size of 2.5 makes a big difference for any collection. And our encoding times are pretty minimal, 15 milliseconds for a half a megabyte file. The biggest file that we encounter are mammogram files, and they can be up to 30 megabytes. And even they are also transcoded within 126 milliseconds. So I have data for about 4 more such modalities. All of these are separate talks of their own as to how this encoding operation works. So any compression itself is comprised of several steps. I will only talk of the first one, which is the block coding, because that is where the original JPEG 2000 is computationally very exhaustive. It takes a lot of time. And what high throughput JPEG 2000 does is it breaks down that first block coding method using rate adaptive parallel layers. And what essentially it does is it says that you have a sequential way, but I'm going to be somebody that does it dynamically, where first I decide what kind of resource allocation you're going to get dynamically, and then we can do the rest of the steps of the compression. So another great thing that comes with using JPEG 2000 or HTJ2K for your images instead of uncompressed is they have hierarchical sublayer construction. So if there is an image, within that image consists 5 sublayers. So for example, you wanted to display a thumbnail of the image, you do not have to store that thumbnail separately. You can just fetch it and fetch the fifth worst quality sublayer and display it when you're decoding it. So that makes it very easy to have to save space. A lot of researchers need dedicated, like my machine learning model works, but it only works on 256 by 256 images. If you put in 250 by 250, it will drop essential information. But this is useful. You don't have to create separate copies of your data sets. You can just have one copy, and you can keep extracting whatever sub-resolution layer you want. So I'm glad, I still have a couple of minutes. I would like to introduce myself. I am Utkarsh. I work at the University of Arkansas for Medical Sciences. And my advisor is Dr. Larry Tarbox. He's done some foundational work with the Cancer Imaging Archive. And my third co-author is Chris Hafey. He works with AWS Health Imaging, and he's the vice president there. He's the primary author of OpenJP.js, and his work has been very phenomenal for our work. Yeah, thank you.
Wonderful. Thank you so much. And thanks for keeping the time. Great timing.
Do I have time for questions?
Yes, absolutely. We have time for questions. Yeah, so it's a great tool for anyone working with image data. So a really great resource. Any questions in the audience? I'm going to start with one. What are your thoughts on using the directly compressed images to do deep learning on the compressed images? Do you think that's feasible? Have you tried that?
So for a deep learning algorithm, it doesn't exactly work on compressed images. To understand an image, it has to decode it. Like you take a file object, let's say it's JPEG. JPEG is compressed, but when you're feeding it, it's feeding the exact image. Like it's learning from the image. So
there are a few tools that can work on directly on compressed images. A few methods available. So yeah, potentially in the future, this would be a great resource using your tool and doing deep learning directly on.
I hope so. For researchers that consume our compressed images, we do give them like decode lines to run. Like, if you're if you're working on Google Colab or Python, we'll give you a shell script to run before it, and you'll be able to access all the decoded images. I am not really aware of somebody that's consuming a compressed image by itself. If you are consuming, you're probably just putting it as like pillow.read, and then you're reading that compressed image. But what Pillow is doing for you is it's decoding it to understand it. Without decoding, it won't be possible to read a compressed image. That's my understanding. I could be wrong.
Wonderful. Yeah. Okay. If there are no more questions, let's thank. Oh, there is a question. Wonderful. There you go.
What do you think is the biggest barrier to adoption?
Oh, anything that's new is like a 50-50 game. Like it's very hard to predict if something is going to catch on. This was adopted by DICOM last year. JPEG 2000 was released in 2000. JPEG caught on. Everybody uses JPEG. It's very it was released in 1994, I guess, and we still use it. So for some phenomenal technology to catch on is very hard at the beginning to predict. The only way to know is for people to have tools. So there's a commercial software available called Kakadu. I don't know how much they charge. I used their directory, and it was all C++, and I don't know it, so I couldn't use it. So this is the open source version of another open source kernel. I don't know how many people are using it. It's very hard to say if this will catch on. It will bring down the size of the archive we have, and 30.9 million images. When we bring it down by a size of 3, it will be a big difference. So we do our work, but if it catches on, I'm not a startup founder. I won't, say a lot of things about the future.
Very cool. Thank you.